Hello, this is Dr. Tesler for Operating Systems in the fall of 2020 at Towson University. Today we're going to discuss Chapter 5 and Process Synchronization. Before we go into this lecture, I want to recommend that as you get to each code segment that we'll examine here, take the time to just pause after the explanation or during the explanation so that you can get your head around the issues. Synchronization is not a simple topic. It's one that requires disciplined thought to imagine one process or thread executing concurrently while another does the same over the same information. So as you go through this lecture, normally we would have this course in person and we have opportunities to discuss each of the synchronization issues, race conditions and deadlock, and be able to sort of tease through any confusion that you might have in class that would give you the opportunity to interact with the material. In this environment where we can't interact together, you're going to need to take a little bit of extra time with each of those slides and in the book to digest the material. I also suggest that you read at least a portion of the chapter, if not all of the chapter, before going through this video. It will help you tremendously. So with that, let's get on to our topics. So just to recap what we should have covered previously and what you should be familiar with is the notion of a thread, what that means on a CPU and what that means in an operating system or in a program. The APIs for threading, pthread, Windows, and whatever, the one for OS X. Then the other multi-threading issues such as signaling, how signals are handled across a process with multiple threads, how you might fork or clone a process and when that's necessary. Our objectives today are to present the concepts of synchronization, to introduce what a critical section is and what the critical section problem is, and how we can solve that problem to ensure consistent data across multiple processes or threads of execution. We'll explore both software and hardware solutions to that problem, and then we'll look at some other synchronization problems and deadlock as well. Throughout this lecture, the term process and thread are interchangeable. All that we're concerned with is, if I say process, that just means one process with one thread of execution, one flow of control. This could apply to multiple threads. The idea is that there is synchronized data, that there is a component of code, the source code that we'll be running, that is shared across processes or threads, and that there is data that must be synchronized between them as well. So our motivation, this is part of your lab. This is a problem that you've already encountered, at least in the lab, though you may not be ready to solve it by the end of reading this chapter and going through this lecture. You should be able to solve that problem all by yourself. So in this particular program, what we have are 5 threads of execution, and we use the pthread API to create those 5 threads in this line here. And their entry points are this count votes function. And each of these counts 10 million votes. It's difficult with so many. 10 million or 1 million votes. 10 million, sorry. And so we should have a total of 50 million votes when this program completes, when the process terminates and all of the threads terminate. When you run this, you realize that that doesn't happen, and that's because of the increment on votes. Votes is a shared variable among all of the threads because it exists in the address space of the process. And as each thread reads votes, the value is updated based on that thread's local variable, local registers when this for loop runs, and if 2 threads execute that increment at the same time, they will conflict, and the result will be shy a vote, at least 1 vote. So our outline for this lecture is to go through the background, the critical section problem, some solutions, then some mechanisms that are higher level to alleviate the developer from solving these problems time and time again, and then on to more advanced solutions, and then some synchronization and some alternative approaches to solving synchronization problems. So our background. Processes or threads can execute concurrently. They may be interrupted at any time, and that would delay the completion of their execution. When processes are executing concurrently, and sharing data, then that view may be inconsistent. So let's say that we had copied a global variable into a function. The global variable may be updated by another process or thread, thus invalidating the copy that we have locally. So we want to maintain consistent copies of data across processes if we want to work on it concurrently. And one of the areas where we want to have consistent information is in the producer-consumer problem, where the producer produces items and the consumer consumes those items, and they both need to understand how many have been produced and how many have been consumed for our factory, our production line to be an accurate reflection of reality. So in the example, we might take a counter, set it to 0, and when the producer executes, it increases that counter to indicate there is something to be consumed. And when that counter is non-zero, the consumer can consume something from a buffer, work on it, and decrement that count, indicating that there is less in the buffer to be consumed and the producer has more availability to produce items. So with the source code from the producer, this is familiar. What's important is we have this counter variable that we discussed before. And for the producer, if the counter is the size of the buffer, there's no room to place anything into the buffer, so it just sits there waiting until that counter is reduced to less than the buffer size. When there is availability in that buffer, then it places into the buffer the next item at the location that is next available. So modulus arithmetic, this you should be familiar with, is how this cycles through the array indices of buffer, which is of buffer size. And then it increments counter to tell the consumer that there is something to be consumed. The consumer, running concurrently, will continue to check counter and see if that value is 0, there's nothing to do, so it has to wait, so it just sits there waiting. And if the counter is non-zero, there is something to be consumed, taking that from the out variable, which it increments after consuming the item, and then decrements the counter. So the problem is that counter in the consumer may be updated at the same time that the producer is updating it. And that can lead to an incorrect value in counter as a result. So if counter++ is implemented as a 3-step process of copying the value from memory to a register, incrementing the value in the register, and then placing the register back in memory, counter minus minus would be implemented similarly with a decrement rather than an increment. That means that when the producer increments the value before storing it back to counter, the register value would be 6 if we started with 5. At that point, if for whatever reason the process is context switched out and the consumer resumes, then the the counter variable in memory would still be 5. So copied to the register in the consumer's address space would be the value 5, decremented to 4, and at this point, the consumer may be swapped out again. And when it is swapped out, the producer resumes and stores its value from register 1 into counter, which places it at 6. Then the consumer resumes later, and it stores the value in counter that it had in register 2, which is 4. So at the end of this process, while it should have been 5 as our correct count, our actual value is 4. So we are going to try to address this with what we call a critical section. And a critical section is a portion of code that only one thread is allowed to execute at one moment. And so if we have n processes and they share the same code, they have a critical section where they might update shared variables or issue IO requests to the same file descriptor. If this section might introduce inconsistency, we will call it a critical section and state that only one of those processes may execute across that critical section at any time. The critical section problem then is to design a protocol such that only one process may execute within that section at the same time. There's a structure that the book introduces for critical sections called an entry section, an exit section, and then what they call the remainder. And it looks like this in concept. The do while is not necessary for our purposes, but it's just a way to illustrate that this section might be resumed again and again and again. So there's the entry section, and that indicates the beginning of our critical section, then an exit section, which indicates the end of the critical section, and then the remainder, which is just code that is not protected. So an algorithm that may solve this for a process PI is as follows. And each of the slides from this point forward will talk about synchronization in terms of two processes, PI and PJ. It will always take the perspective of process I, and any variable I will refer to this process, process I, and any variable j will refer to the other process j. So while the turn is for process j, process I will sit and spin and do nothing. It will wait. Once turn is no longer equal to j, that would indicate that it's I, then it becomes process I's turn to enter the critical section. When process I is done, it sets the variable turn to j, indicating that it's j's turn to run, and continues its processing. Excuse me. From j's perspective, this while loop is a little bit different. It would say while turn is equal to I, wait, and then when turn is set to j, execute the critical section, and then afterwards set turn equal to I. So the slides here, for context, will always talk about the process I as the current context of the process, and j as another process that needs to execute over the same critical section. And j is just a placeholder for the other process, and I will refer to this process. So any solution to the critical section problem of developing an entry, a critical section which only one process can execute, and then an exit section with a remainder has three properties. Mutual exclusion, that is, that if PI is executing in its critical section, no other process can be executing in their critical section, which would be the same code. That progress is being made. That if no process is within the critical section, and then another process wishes to enter the critical section, it will not be postponed indefinitely from doing so. Similarly, the waiting for a process to enter its critical section must be bounded. That there are a limited number of times, that would be blocks or cycles, before the process requesting to enter the critical section is allowed to enter. This demands that every process is properly written, that it obeys the protocol to do so, and that the speed is non-zero of each process making progress, but that relative speeds, they may be different. So one solution that has these three properties is Peterson's solution. And this uses two atomic instructions that must be supplied by the hardware. And an atomic instruction is one that cannot be interrupted. That the entire instruction completes before any interrupt would be allowed to be delivered to any process on the system. So there are going to be two of these atomic instructions, load and store. There are two components of the atomic instructions, load and store. And our example will use two variables, the variable turn, and then two flags that are true or false. And turn indicates which process is being granted entrance into the critical section, and then the flag is the process's interest in entering its critical section. So process I sets flag of its process to true, says that process I is ready to enter the critical section. So again, our entry section is here for process I. It sets the flag to true, and then sets the turn to the other process, process J. And if the other process has indicated that it wants to enter the critical section, and it's the other process's turn, then process I just sits and waits, doing nothing. When process J is done with its critical section, it will set its flag to false, and process I can continue into its critical section. At the end of the critical section, at our exit, it will set its flag to false to allow process J, if it is now waiting to enter the critical section, to proceed. So the way that I think about the particular line of while flag for the other process and the turn is equal to the other turn, I think of this as while the other guy is in his section or it's the other guy's turn, sit and spin. So that's kind of how I think about it. Sorry, it's while the other guy is in his section and it's his turn, then we sit and spin, doing nothing. So we can show that Peterson's solution matches our three criteria, that mutual exclusion is preserved, and that is by our condition on our while loop, that either process I enters the critical section only if the other process is not interested in the critical section, meaning it's set its flag to false or it's never entered, or if its current turn is given to process I. So the process J may be interested in entering its critical section, but if it's not process J's turn, then it is process I's turn. And those are the only two ways that process I will proceed. And since the turn is for process I, process J would be sitting in that while loop, not yet entering the critical section. Progress is maintained because as long as the flag is set at the end, then the other, progress will be made because if J is not within the critical section, then process I may enter, given our initial conditions. And bounded waiting, is met because when process J completes, process I will be allowed to enter its critical section before process J would be able to enter the critical section. And to see that, consider from process J's perspective that it is completed, and it has set the flag to false for itself. It then sets its flag to true, but sets the turn to I. So at that point, I will be permitted to run. So there is one waiting period, which is one critical section execution of J before I will be able to enter its critical section. There is one remaining issue, which is that of turn. That turn may be set to I or J, depending on how each of I and J are interleaved, how they are executed concurrently or in parallel. However, one of them will succeed, allowing us to progress. So critical sections are a well-known concept, and there is hardware support. But most of those solutions are based around the idea of locking. So we protect a critical region by locking it. You must acquire the lock before you can enter a critical section, and then you must return the lock when you are done. Locks could be enabled, critical sections could be protected using locks that disable interrupts to make sure that there are no issues there. But this is generally really inefficient, especially in multiprocessor systems. And as our multiprocessor systems scale, this is not a scalable solution. So instead, we have these atomic operations which cannot be interrupted. And we have two examples that we'll go through in a minute that we use to implement our locks. So the two of them are to test and set, which is a strange concept, and the other is to swap based on, it's to compare and then swap. So the swap is conditional on the comparison. So we'll go through those in just a second. But the general form of our critical section will now look like acquire the lock, execute over the critical section, release the lock. And only one process is allowed to have the lock at any moment before entering the critical section, and then it must release the lock to allow others to progress. So this is, though it is written in C, I would consider this more pseudocode for our test and set atomic instruction. And the idea is that we have some target, and that's the thing that we are going to set after we test it. Testing means, in this case, to copy the value and return it. So the first thing that we do in our atomic instruction, meaning this cannot be interrupted, that it cannot be scheduled out by any process, by any scheduler trying to preempt, that once this instruction starts, the whole thing completes before anything else can take place on the processor. So it stores the value of the target to a local value, sets the target to true, and then returns the target's initial value. How we can use this is our lock is to say we're going to test and set the lock, and this while loop will run, and if the lock was false, that will be the value returned, and we will enter the critical section. As we returned the false value, lock was set to true. So if there's any other process executing the same line of code, it will find true as the value. Only one of the processes can receive the false value. The rest will see it as true because they took place later. As it progresses, the only process that sets lock to false is the one that was able to find it set false in the first place, so it sets the value to false and resumes. The next process that comes along will test that variable to see if it's false, find it false, and proceed through the critical section. To note here, there are problems with this, and that is that of bounded waiting, that if there are 10 processes trying to acquire the lock, it could be that only one of those processes repeatedly gets that lock for an infinite number of times. So this does not work all by itself. We're going to have to do more to protect this one, but we'll get there later. The other atomic operation, again, this is pseudocode written in C so that we can understand it, but this would be implemented as a single instruction on your processor. And we're going to test this value. That is the memory that's being inspected, and we're going to compare it to an expected value. If the value matches the expected value, we will set it to a new value. Otherwise, we'll just return without setting it, but we will always return the value that we found before it was set or if it was not set. So again, compare and swap. We compare value to its expected value. If it is true, then we swap in the new value for value. If value is not equal to expected, we do not swap in the new value, and we return whatever the value was when we enter the instruction. So how does this work to make a lock? We do a compare and a swap on our integer lock that's set to 0. We expect it to be 0, and if it is 0, then we set it to 1. The while loop will be false if upon entering this instruction, lock was false. Since this loop does nothing, we will progress to setting lock to 0 because after our critical section. Because if this line succeeded, if we were able to progress past our while condition, That means that lock was 0 to begin with. That matched our expected value. We set it to 1, but the value returned was 0, which caused our Boolean condition to fail to allow us to enter the critical section. If lock was 1, then we would not have set it to 1 because it would not match the 0, and we would be stuck looping, doing nothing. So once the lock is acquired, the critical section can be executed and then set to 0 to allow other processes to acquire the lock. Again, this suffers from the same problem of bounded waiting for any other process, for processes. So, how do we solve the bounded waiting problem? This is done using, this is one method we could use. So here we have our entry section isn't highlighted here, so we have to figure it out ourselves. This is our entry section, and then here is our exit section, which is much larger. So we have a flag that says that I'm waiting for process I, that's true. And we set our key that yes, we are waiting to true. While we are waiting and we have the key, we try to test and set the lock. So if the lock is set, meaning that it's true, then this loop from these two lines will continue going and going and going until the lock is 0, at which point key will be false and lock will be 1, causing the while to terminate, and we move on to our next line. We are no longer waiting, we are now entering the critical section, which is why we set our flag to false. I'm not going to go through this. You can take a look and you'll figure it out for yourselves, or you figure out the next sentence on your own. But essentially, all this does is find the next waiting process. So it's trying to find any j that is also waiting to execute through the critical section. If it cannot find one, meaning that it wrapped all the way around the end processes waiting to execute over the critical section, set the lock to false so that the lock is not held by anyone. Otherwise, if it did find another process waiting for the lock, let that process have the lock and set its waiting to false. So as process J was waiting for the lock, running this test over and over and over again, by setting J's waiting to false, the while condition fails, and it begins to execute through the critical section, then finds the next process waiting, sets its waiting to false, or just sets the lock to being open. And in this way, the bounded waiting problem is resolved by going from the current index of the process waiting to the next one, checking if that one is waiting, and if it is, allow it to enter the critical section, otherwise keep going. So it orders the process by some numbering that allows it to resolve the bounded waiting problem. So that means if there are n processes, there are n-1 critical section executions that will execute before it is your turn. So using atomic instructions, we can solve our critical section problem. But if we wanted to avoid solving this problem for every program that we write, we would want a data structure that handled it for us. One of those data structures is a mutex, and that stands for mutual exclusion. And these are provided by a library or by the operating system natively. And here we will use acquire and release to be our entry and our exit sections. So acquire and release, these must be atomic. We've seen how we can implement those as atomic operations using our test and set or compare and swap. The book solution requires busy waiting, and that's why we call it a spin lock. So here we have our versions of a mutex, and it says to acquire, and it just has a single Boolean flag that says while not available, just wait. When and that must wait until someone releases the lock, setting available to true. So if available were true for acquire, then the while would never busy wait, it would set available to false, and it would acquire the lock, execute its critical section, and then release the lock, setting available to true. If another process had the lock, while trying to acquire the lock, available would be true, we must busy wait until the other process releases the lock, setting available to true, so that we can fail our test of our while loop and set available to false and enter our critical section. A semaphore is similar to a mutex in that it protects a region, but it is still different in that it has a signaling mechanism built in, that there will be potentially a queue of listeners waiting on a particular semaphore. We talked about this in most of our discussion sections in some form or another. So a semaphore will be represented by an integer variable, and there are two operations on that semaphore, either to wait or to signal. Wait will decrement S, the semaphore, if it is above 0. Otherwise, it has to wait, as we showed for our mutex that we might spin lock to do it. And then once there is capacity, once S has been incremented above 0, wait will decrement it by 1 and proceed to execute. Signaling increases the value of the semaphore. So without considering waiting or proceeding, wait will reduce the count of the semaphore, signal will increase the count of the semaphore. In trying to decrement the count by calling wait, if that value is 0, then that value cannot be reduced, so it must wait until that value is above 0. There are two types of semaphores that may be referred to. A counting semaphore has an integer value, or a binary semaphore has a range between 0 and 1. It is not quite the same as a mutex, but it can service the same functions as a mutex. So one of the issues that you might have is that you have two processes that want to execute in lockstep, meaning process 2 has to wait for an event in process 1 to complete, and that can be done with a semaphore. In this case, they have a semaphore named sync that they've initialized to 0, and after process 1 completes S1, it signals sync, incrementing that value to 1 because it started at 0. Process 2 will be waiting on sync to be non-zero, and that will decrement the value back to 0, and then it can execute S2. So in that instance, we executed P1 before P2. If we reverse it, from P2's perspective, if it starts before P1, it waits on sync. Sync starts at value 0, so it cannot decrement, it must wait. P1 is then executing later, finishes S1, signals sync, which raises the value, and that allows P2 to decrement the value because it's above 0 and proceed to S2. So a mutex and a semaphore are not quite the same. A mutex is a lock, and one person can open or close, can lock or unlock the lock. A semaphore is more of a signaling mechanism, that when the semaphore goes from 0 to another value, 0 to 1, that it will signal, hey, is anybody waiting for the semaphore? I'll let you know. Another conceptual difference is that unlocking an unlocked mutex doesn't do anything, but signaling a semaphore will increment the semaphore, even if it already has a value that's not 0. So they're not quite the same. They're just a little bit different. Though you can use a semaphore with value of 0 or 1 as a lock if you don't have a mutex. So a semaphore needs to make sure that information is synchronized and that critical regions are protected. It must guarantee that no two processes can execute wait and signal on the same semaphore at the same time. So that's moving the critical section problem away from your code into the semaphore implementation itself. We had the previous example used busy waiting in wait to keep checking the integer value, but that must guarantee that capturing the value from memory and comparing it to a register is an atomic operation. And the book argues that this busy waiting isn't such a big deal because it's short. I don't really want to live in a world where my software might behave inappropriately every now and again, but because it's so small, it might not happen very often. So not the best justification in my mind, not in our book. So it doesn't matter. This percentage argument isn't very strong, and we might want to take that with a grain of salt, especially as the number of processes continue to increase. That this justification that one process may be spending a smaller amount of time there, well, now we have thousands of processes spending a little bit of time in that small region, and in aggregate, we're spending a lot of time, which increases our chance for errors. So probably not the best discipline for a programmer. So I wanted to bring that up, not as a criticism of the authors, but as maybe a change in time that we might want to consider, hey, this isn't the best way. So there's another solution here, which is based on our idea of a queue. So we have a semaphore without busy waiting. And this time we have our value, which is still our semaphore's value, and then a pointer to the next process waiting on that semaphore. We must then have two operations that will be provided by the operating system, block and wake up. Block is to block the process, and wake up is to signal a process to wake up. So our semaphore has those two components, our value and our process list. And our pseudocode, roughly, of our semaphore now says waiting on a semaphore decrements the value. If it's less than 0, we're going to add this semaphore to the list. Meaning this process is waiting to execute is waiting to acquire the semaphore. And it blocks. So this is a call to the operating system to move the process from the running state to the waiting state where it's waiting on a semaphore. Signal operates similarly in that it increments the value, and if the value is less than or equal to 0, then we want to remove a process from the list, wake it up, and give it a chance to run. So wake up here, this is to context switch the process back in, or sorry, more accurately to say to put it into the ready state that the scheduler may put it into the running state yet again. So with our concepts of, oops, I apologize, it's the wrong one. Now that we have our concepts of semaphores, we can introduce the idea of deadlock and starvation. So to begin, deadlock is when a set of processes are trying to acquire a resource, and the only way to resolve it is for one of those blocked processes to release that resource. But because all the processes are blocked, it cannot, and so no process can proceed. The simplest example is this two-process example, where process 0 is waiting on S and waiting on Q. If S and Q were initialized to 1, then S would be decremented to 0, Q would be decremented to 0, and try to proceed. If process 1 executes after process 0 executes wait S and Q, process 1 has to wait on Q before it can proceed. That would be a successful operation if it were to occur after the two waits of P0. However, if process 0 executes wait on S and process 1 executes wait on Q, both S and Q have semaphore values of 0. Process 0 then waits on Q, which is of the value 0, so process 0 blocks. That allows process 1 to run, which waits on S. And since S is 0, process 1 blocks. There is no way to resolve that deadlock with just these two processes, because process 1 is waiting for process 0 to signal S, process 0 is waiting on process 1 to signal Q to allow them to proceed. So this is a deadlock. There is no way to proceed. Starvation occurs when, in this case for a semaphore where we had our Qs, if we were to do a last in, first out Q order on a semaphore, then the last process to enter the queue of the semaphore would be the first one removed. And if it was in a tight loop, as we've seen in our examples, then that process would continually wait on the semaphore, signal semaphore, which would in turn just signal itself when it went back to get the next resource. So in that way, it would starve anyone else waiting on that semaphore if we used the wrong queuing policy. So that is a problem with a semaphore. Priority inversion is a way that a lower priority process can prevent a higher priority process from executing. And what may happen is that a lower priority process may acquire a resource. They may wait on a semaphore. A higher priority process becomes ready to run, so it's a higher priority, it must run. And now it tries to wait on that same semaphore. Since it's held by a lower priority process, that higher priority process blocks. Now, as the lower priority process continues to execute and holds that resource, a process of medium priority between the low and the high may become ready to run. And because it's higher priority than the low priority process, it gets to run. And now that medium priority process is running in place of both the higher priority process and the lower priority. Thus, we say that the medium priority process has received a priority inversion. It should not be executing over the higher priority process. The simple solution to this is called a priority inheritance protocol. And what that would say is that when the lower priority process acquired that resource, since it might be acquired by a higher priority process, we're going to elevate the priority of that lower priority process. So there are some classic examples of synchronization that we'll use to illustrate what we've gone through for synchronization. The bounded buffer problem, readers and writers, and the dining philosophers. These are different flavors, and we use these analogies because they occur in programs and in operating systems commonly. So the bounded buffer problem is phrased a little differently than I'm used to, but there's essentially n buffers and they hold one item each. So there are n items that we can store. We then have a mutual exclusion that protects the critical section, as well as a semaphore that indicates whether or not the buffer is full, and then another which indicates which is empty. So the empty one says how much capacity is left, and the full says that the buffer is full. Looking at the producer, this is a little easier. So remember, empty is initialized to the size of our buffer. If empty is 0, then the buffer is full. So this counts the number of empty slots. So we wait on an empty slot, we get it. Then we have our code that must be protected, our mutual exclusion section within our producer. And then when we're done, we release that mutex so that any other process can execute in that section. And then we signal full, increasing the number of items available in full. Full is used by the consumer, and when before it can begin using an item, it needs to wait for some item to exist. So full indicates that a non-zero value in full indicates that there is something to be consumed. Once there is something to be consumed, the critical section is entered after being protected by the mutex, and the next item is consumed from the buffer. When we're done, in the consumer code, we release that mutual exclusion, that lock, and we reduce the number of, we increase the number of empty slots. So the piece that gets a little confusing here is that we have two protections with our semaphores. We wait on our empty, okay, so that means we have to have an empty slot. And then we have this critical section. That means that only one producer can modify the buffer at any time. In addition, no consumer can modify the buffer at the same time. So within our protected mutex, this is where we modify the buffer. What gets confusing is, well, why did we wait on empty if we're just protecting this section? There may be multiple producers now. And here there may be multiple producers, up to n of them, that wish to place items into the buffer. Only one of them can place an item in the buffer at any time. Similarly, there may be multiple consumers. And so that's why we wait to see who will be allowed to modify the buffer to do its producing or consuming, and then our mutex to protect the code that modifies the buffer itself. The readers and writers problem is a different flavor of problem, in that when reading information, even if it's shared, is a non-destructive operation and should be and can be done by any number of readers at the same time. However, when something is written, the effect will be different. That the effect of that writing will impact the other processes. So here we're going to allow multiple readers to read at the same time. But once we write, then we need to stop the readers, or we need to delay the readers until that write is complete, and only one can write at that time. So we have our shared data, and we have one semaphore for read-writing. That's a read-write mutex. And then another semaphore for just reading, that's initialized to 1, and then our read count. Those are the number of readers. So the writer must acquire the read-write mutex and perform its writing, and then when it's done, it signals the read-write mutex. Very simple. The reader is far more complicated. The reader waits on the mutex to the reading mutex and increases the read count. If it is the first reader, because read count is initialized to 0, then it also tries to acquire to the read-write mutex. So now if this is the first reader, it has acquired the read-write mutex, and then it signals all of the other readers. And this mutex is just to protect our read count. Reading can be performed. The only protection is around that read count. Afterwards, since it needs to access the read count again, it waits on the mutex, decrements the count. And if it is the last reader, then it will signal the read-write mutex to allow the writer to go. So this first and last portion, because the first and last protect all of the readers who went to read from being impacted by the writer until all the reading is done. And that meaning that if they were on queue to read from our wait on that read count, then they will get the opportunity to read before the writer will go. So we just looked at our first variation, that no reader is kept waiting unless the writer has permission, and the second variation is that once the writer is ready, it performs the write immediately, and then the readers are resumed. Both of these can lead to starvation, and there are advanced read-writer locks that will avoid starvation, but at least you should be able to identify how this can starve readers or writers at this point. So the last problem we'll look at is the dining philosophers problem. And in this case, we have 5 philosophers, and they would like to eat this rice at times. But each philosopher has a set of behaviors that they will sit and they will think, and after some time they will become hungry, and they will want to eat from the rice in the middle of the table. To do so, they need to pick up a chopstick to their left and a chopstick to their right. But there is only one chopstick between each philosopher. So the problem is that if I'm the southernmost philosopher, I need the southwest chopstick and the southeast chopstick, and that may be held by the southeast or the southwest philosopher. I cannot eat unless I have both. So if we take a naive approach, to this problem, and the philosopher I has the chopstick to their left indicated by their index, and then the one to their right, their index plus 1. If there are 5 semaphores, simply waiting on each semaphore, eating, and then signaling on each semaphore, and going back to thinking. What is the problem with this algorithm? And I'll give you just a second to think about that. Well, this is a multi-process system, so we have multiple processes running, and if they all happen to run their weight on their semaphore for their left-hand chopstick first, and they all run that weight at the same time, then everyone picks up their left chopstick, and nobody can get their chopstick at the right, and everybody starves. So this is an example of deadlock, and how we might solve this problem is to reduce the number of philosophers. Just take one out of the table. He doesn't need to eat. We're going to starve him to death, so we'll just take him out of his chair, and that's done. The other is to allow a philosopher to pick up both forks only if both are available, meaning that we would put these into a critical section, or we might try to assign odd number philosophers to pick up on their left first, and then even number philosophers to pick up on their right first. So these are alternative options for solving this problem. There are more. There's a complete solution in your book, which should help to understand how you might address this. So the problem with semaphores is not actually a problem with the semaphores. It's a problem with using the semaphores. That they require discipline. So if we signal before we wait on a mutex, that's going to lead to multiple processes entering their critical sections at the same time, and that's what we don't want. A critical section is for one process at one process at a time. Similarly, we may wait and then wait on a semaphore, and that would allow only one process to go into the critical section. Then when it waited again, no other process would be able to enter because it was not signaled. And the last way that we might abuse a semaphore is to forget to wait or signal, or both. So if we don't use our mutexes to protect our critical sections, well then we just executed our critical section without any protection. And then also deadlock and starvation that we've gone through just by misusing or misordering our semaphore wait and signals. So to take the problem out of developers' hands, a higher level abstraction is that of monitors. And a monitor is essentially limits any process to executing or using the shared variables within the monitor to one at a time. So any process trying to access the shared data or perform operations on that monitor gets placed on a queue and then gets processed through that queue to execute those operations or access the data. It includes condition variables, and a condition variable is very similar to a semaphore. in that when it calls wait, that process will then just sit there and wait at that execution point until it is signaled by another process, and then signal will resume any of the processes that invoked wait. If no one is waiting, then there's no effect on that conditional variable. So within our monitor, we might have condition variables that are processes that have decided to yield control by waiting, and then other processes which allow them to resume. So when we use a condition variable, if P invokes signal and process Q is suspended on wait, what should happen next? And the decision here is which gets to run. Because it's within the monitor, which says that only one process can execute at any time, the choice is to either resume Q, wait for P, or resume P, and Q must wait. So signal and wait is one approach, and that says that P waits until Q leaves the monitor or waits for another condition. Signal and continue is that Q would wait until P leaves the monitor or another wait condition. So there are pros and cons to either side, and the concurrent Pascal, which we won't use in this course, is a compromise. But there are implementations that you may be familiar with. C# and Java are likely those that you've seen, such similar condition variables. So we can use a monitor to solve our dining philosopher. And I'm going to skip to how we use the philosopher first and then go back to the components piece by piece. But importantly, there's a state and a condition for each of our philosophers. And the philosopher will pick up and then put down. So it cannot put down without picking up. And to match our scenario, a philosopher will pick up, eat some food, and then put down their chopsticks. So let's take a look at pick up. So pick up refers to philosopher I, and that's when they're picking up their chopsticks, that says that they're hungry. And then they're going to test. And if that test is successful, and if the test tells them that they are eating, then they will proceed. Otherwise, if they are not eating, they will tell them they will suspend themselves, they will wait. So let's take a look at test, because that is the next portion of pickup. But importantly, pickup may put the philosopher I into the waiting state. So what this says, what our test does essentially is look left and right and see if the left and right parties are not eating. If they're not eating and I am hungry, then I will now move to eating and I will signal, saying that it's time for me to wake up, time for I to wake up and begin processing again. If I was not waiting, nothing will happen, and that's great. So it gets to proceed. However, if I was waiting, then it would wake up here and see if itself was waiting. It would wake up here and continue executing. When I is finished, then the first thing it does is change its state to thinking, and then tests its neighbors, its left and right neighbors, to see if they need to be woken up because they're waiting here. And the only piece that's left for each of our philosophers is that they need to be initialized to their thinking states in the beginning. So this would allow our 5 processes to execute and be protected by the monitor to ensure that only one of them was executing any of this code at any time, and then once they found themselves in a state where they had to wait, they would put themselves to waiting, and when another philosopher was done eating and going back to thinking, it would wake up the appropriate processes. So the monitor can use semaphores to implement the operations without any intervention by the developer. So this means that if you had a semaphore, it could build in its compiler or out of its library the following code to surround the body of the function. So first, we protect every procedure with a single mutex. And at the end, we have a next count and a signal for next. Now this is a little out of place yet. We haven't gotten there. So we're just going to hold off for just a minute. But essentially, if next count is 0, every time we invoked f, we would wait on the mutex first and then signal the mutex that we're done. So just providing critical section protection around f. Next count and next are part of signal. We'll get there in just a second. So this is, but the signal and waiting on the mutex assures that we have mutual exclusion. The next count and the next semaphore are related to our conditioned variables. So when we have a conditioned variable, that we then generate two additional components, a semaphore for variable x and a count for x. When a process waits on x, it increments the count, this count variable here, and because we're in a monitor, it's the only one accessing it, so we don't need yet another semaphore for it. And then it checks the next count, and if that value is non-zero, then we signal on the next semaphore. Otherwise, we signal on our current mutex. Why we do that, we need to take a look at wait. So we will signal one of two mutexes, and then we will wait on the x semaphore that's created for the variable. And after that wait returns, then we can reduce the count. So the important piece of our wait is that we incremented our count of x count, and then we waited on the semaphore, which is initially 0. So the first time that we call wait, the semaphore will be 0, and that causes us to wait at this line, and x count is non-zero. The second call to wait before any signaling, count will be 1, we'll increase it. Again, we will likely signal on mutex and then wait on the semaphore. But let's take a look at signal then for the last piece. So if the count is greater than 0, which occurred because there was a process waiting on this variable, increase the next count. Strange, we'll get there in a second. And then signal on that semaphore. Signal on the x semaphore for the variable, wait on the next, and then reduce the next count. So let's consider signaling when x count is 0. And x count is 0 when there is no process waiting on this condition variable. So nothing is done, no changes. However, if there is a process waiting on x, x count will be greater than 0. Next count is then incremented, and we signal on x semaphore. Signaling on x semaphore will cause the process waiting on it to resume and reduce the x count. At some point, that process will be done. It will leave. Meanwhile, the process that signaled was waiting on next. And when next is signaled, the next count will be reduced to 0. So where did that happen? How does that work? That will occur either by signaling next from another method being invoked at the end of at a method waiting on the mutex, or after we wait, we reduce the count. So the process that signaled the variable will be waiting on next. Next will be signaled because next starts at value 0. It will be signaled either by a function call being completed, that's when we will signal, or by a process waiting on that same variable. And after it's received that wait then the next count will be decreased and the process that's signaled can continue. So signaling, in this case, will cause the process to block until something else is completed, if there was something waiting on it. And we knew that something was waiting because we would not have been waiting if there was an X count that was greater than 0. So when we decide to resume a process within a monitor, there might be several processes queued on a condition, or there might be several that are waiting to enter into a function, and first come, first serve, or first in, first out may not be adequate. And so we might adjust our wait to take a condition, and that condition will be a priority. So in this case, the process with the lowest number is the highest priority, and that one's scheduled next. And the example that we use, that is used in the book, is that the t parameter here is the amount of time that this process will hold on to that resource. So here, if we then said the lowest value gets to hold on, gets the highest priority for accessing the resource, then that corresponds to the shortest amount of time that resource would be held. So this is saying, if your job is shorter, you get to go first on this resource. And that can clearly lead to starvation, because if a bunch of small short jobs come in to access the resource, then the long one will never be serviced. So we can implement our allocation of a single resource in a monitor by using a variable busy, and we say if we go to acquire that resource, if it's busy, then we have to wait for a specific amount of time. This puts us in our priority. As we just mentioned before, the shorter one will be higher priority and therefore service first. And then when we're done, we'll release it. We'll say that we're no longer busy, and we'll signal. Then everybody that was stuck on the queue at this moment, only the one with the smallest time will be resumed. So the book may discuss Solaris, Windows, Linux, and pthreads. We're not going to concern ourselves with Solaris, and we'll make a brief pass through Windows and Linux and pthreads as well. If you're interested in the facilities, you have the documentation that you can go into in more detail. But in general, interrupt masks are how we prevent access to shared data from being a problem. So we create critical sections by masking interrupts. And as we talked about earlier on multiprocessor systems, that can be that doesn't scale well, so spin locks will be used instead. And a thread that is spin locking cannot be preempted. So there are then dispatcher objects, which are userland variables that provide mutex and semaphores, and they may use spin locks or mask interrupts to do so. But again, we don't really have access to the kernel. We have access to the API, so you can take a look at the API and the mention in the book of how that works. Linux didn't bother with this before because it just disabled interrupts before version 2.6. So within the Linux kernel, critical sections just simply disabled interrupts and didn't scale. Now in later versions where the kernel itself is fully preemptive with semaphores, atomic integers, spin locks, and then reader-writer versions. So even on single CPU systems, the spin locks have been replaced by enabling and disabling kernel preemption. pthreads, again, is an API, so it provides those mutexes and condition variables. Some you might be using for your labs, which you have the documentation for in your book as well. An alternative to critical sections as an idea is our transactional memory, OpenMP, and functional programming. So what we've been talking about with critical sections is to provide consistent information across processes, that the data remains consistent. And one of the observations of modern programming is that we're protecting code, we're not protecting data. And it may make sense to protect data because that's the thing that gets out of sync. So how can we do that with transactional memory? And transactional memory comes from databases, and it says perform this set of operations on these rows in the database, or don't perform any of them. So by guaranteeing that the memory transaction is atomic, even if there are multiple operations, that they all have to take place or none of them do, that takes away the onerous task of synchronization on behalf of the program writer, because they've said, okay, this is a transaction. I know that when it succeeds, my information has been correctly updated. If it doesn't succeed, then I'll try again until it does. OpenMP addresses critical sections by taking all of the work out of the developer's hands and just says pragma critical. And that means that only one thread can execute the block associated with the critical segment. So we haven't protected data here. We've protected execution yet again, but the way that it does so is by limiting only one thread to execute in the critical section at any time, without requiring the user to implement their own semaphores. Functional programming languages didn't set out to solve this problem, but they do so sort of as a product of their design. So the paradigm of a procedural language versus a functional language is that the functional language, a functional programming language, doesn't maintain any state. And that's the exact opposite of an object-oriented programming language, where the object, you would influence the state of the object. So variables, once they're created, can't change state once they've been assigned a value. There are some types of objects in Java that you might declare as immutable, meaning once they're created, they can't be modified. And if all of your objects were that way, then Java would be a functional language. But there are other functional languages. Erlang and Scala are examples of those. And because once the object is created, or once the data is created, it can't be changed, then there's no concern about consistency between processes, so they've completely avoided the problem. So back to deadlock, which we discussed a little bit earlier. And to achieve deadlock, there must be a set of processes, each holding resources, and at least one process is holding a resource that another one of the block processes needs to proceed. So if we have two hard drives and process 1 and process 2 each hold one of the drives, and one of them needs the other, then we cannot move forward. We saw this example earlier, where if process 0 acquires A and B, then process 1 can't proceed. But if process 0 acquires A and process 1 acquires B, then process 0 can't proceed and process 1 can't proceed. Similarly, if we had a one-lane bridge and two cars entered the bridge, then nobody could proceed because one of them would need to back up to let the other proceed. And if they did so, then let's say that the south lane decided to back up and the north lane kept progressing. Well, maybe only cars from the north lane keep going and nobody stops for anybody in the south, so everybody in the south is starved. And deadlock, in terms of user programs, is typically not handled, it isn't tracked by the operating system. It's left to the developer. So here we see that same problem that we might encounter for deadlock again, that acquiring two locks out of order would lead us to a deadlock scenario. And this is using pthread, and I suggest you use this as an example maybe for working on your lab. So for deadlock to arise, there needs to be 4 conditions. First is that there's some form of mutual exclusion, whether that be a semaphore or just a mutex, that a process is holding onto one resource while another is waiting to acquire that resource, and that resources cannot be preempted, meaning that resource can only be released by a process. A process can't be forced to release it. And then there is circular waiting. That means that among the set of processes, a process is holding a resource that a later process is then depending on being released for it to gain all of its resources. One of the tools that we can use to identify potential deadlocks is what we will call a resource allocation graph. And in a resource allocation graph, there's a set of vertices V and edges E. There are two types of vertices in V. There are resources, denoted by an R, and processes, denoted by a P. When P is requesting a resource, there will be an edge from P to that resource. If P has been granted that resource, then there will be an edge from that resource to P. So if we want to take a look at our visual elements, we have a process represented as a vertex in a circle, a resource with 4 instances in this case, meaning there's a capacity 4, so a semaphore maybe with starting value 4. And then when the process requests a resource from R, in this case Rj, if there were none to be allocated, then this would be a request. However, if it's able to acquire that resource, then the edge is drawn from the resource back to P. And so the first one of Rj is given to P. So in our graph, when a request is being made, if it can't be satisfied, there'll be a request edge. If the request can be granted, there'll be an acquisition edge, or an assignment edge, I'm sorry for the terminology. As an example, we have 3 processes, and process 3 has been assigned resource 3, process 2 has been assigned resource 2 and resource 1. Process 1 has been assigned resource 2 and is requesting resource 1. But since there's only one resource, process 1 is by necessity blocked. And when process 3 is done with resource 3, it will release it. That means that process 2 can acquire it. Process 2 then can continue and complete its operation and release resources 2 and 1. Releasing 1 will allow process 1 to complete, so everyone can progress. However, if process 3 were to try and request a resource for R2, since they are held by process 1 and process 2, process 3 is blocked and everybody is blocked. And we can detect this by noting that there is a cycle in our graph. And there are 2 cycles here. From R2 to P1 to R1 to P2 to R3 to P3 back to R2. And there's another cycle from R2 to P2 to R3 to P3 to R2. And because all of the resources are consumed, this system is deadlocked. However, we have a cycle here with resource 2, P1, R2, P1, R1, P3, R2. But we can resolve this deadlock. We can resolve this, and so there is no deadlock, and that's because P4 is holding on to resource 2. So P3 is blocked waiting on R2, of which there are none, and P1 is waiting on P3 because it needs R1. So if P4 releases R2, then P3 will have its request granted, P3 can complete. P1 will then be able to acquire R1 and complete. Similarly, if P2 were to release its resource, P1 could continue. So to summarize, if a graph contains no cycles, then there can't be a deadlock. But if a graph does contain cycles, then there may be deadlock if there are an insufficient number of resources. But if there are sufficient resources, there may not be deadlock. So how do we handle deadlocks? The first is to ensure that the system will never enter a deadlock state. That's through deadlock prevention or avoidance. And to do so, we need a priori information about the resources that each process may request. And in an interactive operating system, that may not be knowable information. We can allow the system to enter a deadlock state, detect it, and then recover, or we can just ignore it. And that's typically what we do, is ignore it, because we leave those problems up to the developers to solve for themselves. So for this lecture, we wanted to present the concepts of process synchronization, and here we're talking about data synchronization. We want data to remain consistent across processes. We introduced the critical section problem. So we have a definition of a critical section, which is that one process can enter that critical section and no others. And how would we implement a solution to ensure that only one process is executing over its critical section? And through that critical section, then we can ensure consistent data manipulation and consistent data across processes. We talked about some software and hardware solutions to the critical section problem. If it's software only, we're going to busy lock. Otherwise, we're going to have those atomic instructions to allow us to build our more abstract operations. Then we looked over some classical process synchronization problems, bounded buffer, reader-writer, and the dining philosophers. And then we wanted to go over a little bit more about deadlock detection and what the concept was. So with that, I will leave you in this longer video. I do apologize for the length, but I do think that you'll probably need to spend some time going back to it. Please do take the time to make sure you understand the code segments, go through the book, probably put some questions up in the discussion forums on Blackboard, and that way you and your fellow students can work through and understand how we address each of these issues through the code and the examples that are given. So with that, I look forward to seeing you in the next class. Thank you.